Yes. Linear density is the mass divided by length. And, as it so happens, while you were taking the test, I took 132 centimeters of string and found the mass of it. The empty mass is, this was the reading in order to have it set at 0. This basically, we need to subtract that from this in order to get the value. So the mass, so the linear density of that string, and I am assuming that that string and this string are from the same lot and same material, because they felt and looked like it. The mass of the string, well, the mass of the string is going to be 1.09 grams minus 0.11 grams. The length, 132 centimeters. That is 0.98 grams over 132 centimeters. Unfortunately, these are not particularly convenient units because our tension was likely we could put it in newtons. So 0.98 grams, how many kilograms is that? All right, and then 132 centimeters into meters.
1.32.
And therefore, the linear density of this string is what?
.00074.
0.00074.
Yes.
And units?
kg over meters.
Yes, kilograms per meter. All right, so that's the linear density of the string. Recap, mentioned that, we did that last week too. So the tension in the string is based upon, well, this is what we're considering equilibrium. It does not seem to be moving at all. Acceleration looks like it is 0. And so therefore the tension in the string here should be equal to the weight here, because I got two forces acting on that connection. There's the weight pulling down. Actually, two forces acting on this mass. I have tension acting up, weight acting down. If it's in equilibrium, they will be equal. We are making the assumption of an ideal string here, and at this point, it's probably pretty legitimate. It's not until we want to go to much higher harmonics that it becomes much shakier assumption. So the weight of this should be the tension in the string. So let's get rid of some of this information. So let's see, we know that mu, the linear density is 0.00074 kilograms per meter. And that's the square root in our case here of tension divided by the linear density. All right, so we have the wavelength over there. The wavelength was 0.813 meters. 813? Let's figure out what this is hanging here. this on it, just so that the thread doesn't go shooting through that. All right, I've already found what the offset is of 0.11 grams. And I would expect this to be, I think those are 20, somewhere around 220. Oh, no, sorry, somewhere around 240. Whoops. All right, so 248.43. So the hanging mass, 248.43, is that what I said? Minus the 0.11, so we end up with 248.32 grams. Of course, we're cool, so we put it into kilograms. So how many kilograms is that?
2.4, no, 0.24.
There we go. I need to find the weight though, because the weight of it was balanced out with the tension. So what's the formula for weight?
Mass times M times G.
Okay. And because this is an actual experiment, not a board problem, G 9.798 meters per second squared. So what do we get as that is the weight, and therefore that is the tension in this case?
Three,
33536 units?
kilograms times meters over second squared.
Yeah, that's actually legitimate. What's the shorthand? Yes. But if you put down kilogram meters per second squared, I would accept it. All right. So let's see what we have here. I think two. Okay. Sorry. Side there. We have all that information. We've got one there. So I know that the wavelength, darker than that. I know that the speed is equal to the wavelength times the frequency, which is also equal to the square root of the tension over the linear density. I can find the speed of the wave, because I know tension and know linear density. So the speed of the wave would be the square root of 2.4333536 divided by 0.00074. If someone would be kind enough to do that.
That's 3,288.
Did you do the square root?
No. 57.35.
57.35?
It's a longer number, I rounded up.
That's fine. Anyone else got the same? That was Eliana, did you not?
I did.
Okay. Units?
Meter per second.
Yes, we're finding the speed, because we put everything into the standard units. Newtons, kilograms, meters, seconds, and so forth. All right, so we have the speed of the wave as it's shooting down the line and back. I'm trying to find the frequency. I know that this number also equals the wavelength times the frequency. We've already found the wavelength over here. So I have 57.35 meters per second. That, we know what the units are, is equal to 0.813 times the frequency. Squeeze them in, that's meters per second, and that's meters.
70.54.
You're at 70.5412
5412.
units.
Hertz. Hertz.
Yes. Give myself a little bit more room there. So we got about 16% error. The actual frequency is based upon the frequency of our AC current, which is 60 hertz. So percent error would be 70.5412 minus 60 divided by 60, which is approximately 1/6. That's about 17%.
17.56. No, yeah,
17.56?
57.
No bragging rights on that one. But I've gotten worse in classes before. Questions about these standing waves? All right, let's take a small little break, and then we'll come back and look at different standing waves. We'll try to figure out what the speed of sound is using this. And it has happened again for the second time. There's a question that everyone got right. The first one. Years ago, as they were coming in, I was looking at that first one just to see if there was some problem that everyone got right. And so far, everyone did. There's a class of, I think, 25. The last person who came in, who handed it in, missed it. So close.
Did we do better than the first time?
I hope so. I don't have all of them memorized. So, but the little bit that I saw, it seemed better. I would hope. All right, so write this over here. Oh, okay. Squeeze in here. Fixed in node. Free in. All right. I'm trusting all of you can hear that. All right. We're now going to take a look at one fixed, one free end. And so an example of that when you're dealing with sound waves would be the water tube. That I've got water basically from the tube up to here, and there's a kink in there. All right, water level's rising. So I've got a water level right here, that is a fixed end, and then I have an open end over here, that's a free end. So sound waves are going to bounce down, hit the water, bounce back up, and there'll be some interference. If the water level is the right height, then we will get a standing wave. Now, the simplest of that, of the one fixed, one free end, well, a fixed end, as I wrote over there, means I have a node. A free end means I have an antinode. So that would be the simplest. This would be the first harmonic. The next simplest, again, fixed at the bottom. I add a half a wave every single time. Badly drawn. Let's see if I can do that better. This would be the third harmonic. Now, if you're looking at old tests, I sometimes refer to this as the second harmonic. Eventually, I was convinced that I was wrong on those. So this, for the one fixed, one free, technically, it's just odd numbers for harmonics. It's the second one. It's called the third harmonic. The next one drawn, but hopefully you get the idea. And so this would be the fifth, and then the seventh harmonic. So each time we add a half wave, same as before, in the same sense that last time we added a half wave every time we went to the next harmonic, same is going to be true for two openings, or two free ends. All right, so if I added a half a wave going from here to here, so half a wave, that's half a wave right there. How many waves is this?
Four.
This is a quarter of a wave. How many waves is this?
Yeah.
We added a half.
Yeah. It's a half, right?
Pardon?
Isn't it a half?
No, it's not a half. If I have a quarter wave and add a half wave to it,
Oh, okay, 3/4.
say it again?
5/4.
And the fact that it goes from 1 to 3 to 5, first, third, fifth harmonics, there's a connection there. And this last one,
So,
and the 51st harmonic,
4/4.
okay, I heard that over 4, 51 over 4 wavelengths. All right. So this tuning fork here has a frequency of 320. If you're not convinced, that sounds like 320, right? And fortunately, it's printed on there.